We have analyzed several regular polyhedron. Everyone may feel it is not easy to imagine them in 3D space. This convex polyhedron contains some regular patterns to help us to remember. How do this image look like? Actually, Euler had already studied on convex polyhedron. Besides, we also know that Euler's theorem may help us to memorize edge, face, and vertices relationship. Euler's theorem described that any convex polyhedron, the number of its corresponding vertices added up with the number of faces minus the number of edges will be equal to 2. Therefore, we managed to analyze that knowing how many edges and how many faces, the number of vertices can be calculated directly. Similarly, for convex regular polyhedron, it has to ensure that each face is a regular polygon, and for a plane polygon, there is such a conclusion. The sum of its inner angles is equal to the number of vertices minus 2 multiplied by 180 degrees. Corresponding to each face, how much is the angles of the regular polygon vertices? After having these thoughts, we have designed a very useful concept to help us analyze the convex polyhedron. We focus on vertex. Its vertex will be connected with several face angles. We can then take these face angles, accumulate all of them together to get a sum. The difference between 360 degrees and the sum, we gave it a name as a complement angle. For this kind of concept, we may not be familiar with this idea. Actually, it was reached by Professor Liansheng Huang in Tsinghua University. Why this concept is very useful? Because with this concept, we can efficiently analyze the characteristic of corresponding convex polyhedrons. First, it has a theorem. We can prove it based on Euler's theorem. It could be stated as, for convex polyhedron, the summation of all the complement angles is exactly 720 degrees. The detailed proof you can practice by yourself. We will first take a regular tetrahedron for verification. First, we have a new concept. Complement angle means that 360 degrees minus the sum of association angle with a vertex. Inside regular tetrahedron, each face is a regular triangle. The inner angle of the regular triangle is exactly 60 degrees. How many inner angles are there for each vertex? There are 3 inner angles. The summation of them are exactly 180. And this time each vertex, its complement angle is 360 minus 180 equals to 180 degrees. Then what are the total summation of complement angles for 4 vertices? All the complement angles for each vertex is 180 multiplied by 4, which is 720 degrees. It is the same as what we have said in complement angle theorem. We then ask a question directly, and this time we can take a regular polygon to build a regular polyhedron. If we use a regular pentagon to build a regular polyhedron, how does it look like? Then we can analyze what is the inner angle of each regular pentagon. We know that in an equilateral polygon, the summation of its inner angle is v minus 2 times 180. For regular pentagon, it is phi minus 2 times 180. All 5 angles are the same, therefore each inner angle is phi minus 2 multiplied by 180 divided by 5, exactly 108 degrees. Means for each vertex, its face angle is 108 degrees. How about the complement angle? And this time we use 360 minus a number times 108. Meaning to gather a smaller number, we will use 360 minus 3 times 108. The obtained complement angle is 36 degrees. So what does it mean? It means that for each vertex, there should be 3 inner angles. Each inner angle is 108 degrees. Since the complement angles are known already, and know that all the summation of vertex complement angle is 720 degrees, then how many vertices are there? I will directly take 720 divided by 36. We'll then get the number of vertices. In total, there are 20 vertices. And we also know that each vertex needs to connect with 3 inner angles. one vertex contains 3 connected edges, where the repeatability is 2. Therefore, how many edges are there? Actually, it used 20 times 3, then divided by 2. In total, there are 30 edges. Then where the vertex is connected to how many faces? It contains 3 related face angles, where the repeatability is exactly 5. Therefore, what we have calculated should be 20 multiplied by 3 divided by 5 is 12 faces. Up to this point, I would like to ask, if we use a pentagon to build a convex regular polyhedron, it should be a regular dodecahedron. Actually, in return, if we know this regular dodecahedron, if each face is a pentagon, we can completely use summation of complete angles for a system to analyze how does regular dodecahedron look like. Similarly, we can see that through this complement angle concept, we all know each inner angle is 108. Therefore, each complement angle should be 36. Corresponding to each vertex, it should contain 3 inner angles connected with it. And this time, 720 degrees divided by complement angle equals to 20 vertices. We can find out that in a regular dodecahedron, there are a total of 12 faces, 20 vertices, 30 edges. If we want to build the regular polyhedron with the most faces, what kind of the convex polygon will it be? For the inner angle is 60. Then 360, as far as possible to minus out 60, it should manage to minus out 560. Therefore, a vertex should corresponding to 5 inner angles, whereas its complement angle is 60. Use 720 divided by 60, which means it contains 12 vertices. 12 vertices, each vertex will be connected to 5 edges, where the repeatability is still 2. Therefore, 12 multiplied by 5, then multiplied by 2, exactly is as 30 edges. Each of the vertex needs to connect with 5 faces. The repeatability is exactly a triangle. Therefore, its solution is 12 multiplied by 6 divided by 3. In total, there are 20 faces. We do not need to draw out the exact image. We have already known that for the icosahedron, it contains 20 faces, 30 edges, it was 12 vertices. Each vertex contains 5 triangles next to it.